Okay, so your next assignment requires you to implement a remote procedure call, implement a component of remote procedure call, not the whole remote procedure call. And to implement a component, you've got to know how the rest of the components in Gypsy are going to fit with your component. So this is going to be in Gypsy, because Gypsy is meant for this such customization. So what we're going to do today is give you an idea of the structure with which you're working, so that you know how your component fits. Okay, and that's for your assignment. From a global learning point of view, you will understand how you might want to architect an RPC implementation. Okay, so you learn about the other components, not just to make them fit with your component, but just to understand also how the components in an RPC implementation should fit together. Okay, so part of it is, you know, how it's just done, whether you can argue for it or not, and part of it is how it should be done. Okay, where you can argue for how things are being done. So we want to architect our RPC implementation, and we learn about architectural principles in software engineering. So what's an architectural principle that you know from software engineering that we might want to apply to an RPC implementation, so that we get the right shoulds in there? So what might have you learned in 401? What might have you learned from me in earlier lectures? And what might have you learned in any design patterns courses? Yeah.
Well, the simplest one is probably the proxy should be singleton. So, you only have one proxy for one instance.
Okay, so that's an interesting thing, that you should have only one proxy for one remote object. By the way, does RMI follow that principle?
I mean, like, shouldn't it be like one singular remote object, right? You can have many proxies.
Okay, so there are two things. Okay, so there are three things going on here. Firstly, you said there should be one proxy for each remote object. Does RMI follow that? Even if it followed that, what Nick is saying is that you might have multiple remote objects of the same class, in which case you'd have different proxies for the different classes. So you'd have different singletons. Okay, I mean, sorry, you would have different instances, so it would not be a singleton of that class. So as it turns out, in Gypsy, I did a lot of work to make that happen, but I don't believe in RMI that happens. Okay, so I can do lookup twice on the same object, and I believe I will get two different proxies each time, because what happens is that the server sends a serialized copy of the proxy it has, the RMI server sends a serialized copy of the server it has, and you get now two different things. Okay, so that principle is an architectural principle to some degree. When you talk of architectural principle, you're talking of how you break up your code into classes. So you're here saying that, if you have a class, put some restrictions and use it in a certain way. So that's certainly an RPC implementation principle, but it's firstly an RPC specific thing if it's a principle for class decomposition, and it's not really a class decomposition principle. So when we talk of architecture could be many things. I mean, architecture we use in building architecture, and architecture we build in software also. But we mean really how to decompose your code into classes. Yeah, Nick?
What I thought was, in the core procedure call, the remote procedure call, and the handling for messages coming around, you would want some sort of observer pattern. You may want some sort of observer pattern that would sort of not that would take care of the things really, like anytime instead of calling.
Okay, so what you're saying is very interesting. You're saying that when a message arrives from another computer, there should be some observer pattern there.
That gets waiting up and calls whatever handler for that method for that message after.
Okay, rather than having an explicit receive?
Yes.
Okay, that's interesting. Do you know of any IPC system that has that?
Like select call.
Select call, you think that's observer pattern? Yeah, okay. Yeah, so select call works with the explicit receive, right? You do explicit receives.
Yeah.
Okay, but that's interesting. So you're saying, in general, I think you're on the right plan that when we talk about breaking up code into multiple classes, we should talk about patterns. Because design patterns talk about how classes cooperate with each other. Okay, an observer pattern is certainly an important pattern, and when you talk of incoming messages, it's good to have observer patterns there, and maybe you want multiple observer patterns there. Okay, and we'll see why that may be the case. So that's good. So patterns, observer pattern, anything. What do you think is the basic principle behind patterns? All these patterns are trying to follow a certain principle, certain software engineering principle that's really independent of any piece of software that you're looking at, whether it needs an observer or not, whether it needs factories or not, whether it needs model view controller or not. There is just this one principle that's guiding the design of patterns. Open close principle meaning so you're saying open source code versus closed source?
Yeah, that was.
So that's interesting. NPR has TED Talks. NPR has TED Talks, and they were talking about why Gopher, a tool from Minnesota, didn't make it because they decided to become closed and not open software, and that's why the web browsers took over. So certainly, if you're going to have software that you want people to use, allow it to be modified by others. Okay, so that is open source, right? And actually, open source software sometimes conflicts with what I'm talking about, because in open source software, you're saying you don't like something, just change my code. A good architected system, I claim, doesn't have to be open source. It would say, you don't like something I want, just make this runtime call, and you can change the component. You don't have to deal with my source code. You don't have to deal with my comments or lack of comments. So sometimes open source is the way out when you haven't architected really well. Okay, but if you want things to be changed, I mean, certainly in this, in your assignment, you can use Gypsy as a black box, I believe, and it'll all work. You don't have to ever change any piece of. You don't have to ever look at the source code unless you're doing debugging. Okay, Sam.
Maybe like separation of concerns.
Separation of concerns. So what does that principle say?
Basically, if a piece of code has a task, that task should be decoupled from something that does another task that's independent.
So if there are two tasks that are independent of each other, then do what?
They should be separate classes.
They should be separate classes. And what is the definition of two independent tasks?
I guess.
If I have a counter and one method increments the counter and the other one decrements the counter, are they separate tasks?
No, they're kind of coupled to the same count. I guess they share the same core object, maybe.
So it gets a little tricky, yeah. People say this principle, and this is exactly the principle I was looking for. But it's a little tricky what it really means. Nick, you had something?
No, I was thinking
Okay.
when you say you want to you want to change the behavior of the code without changing the code directly, I was thinking like you want some sort of extensibility.
You want extensibility, and you get extensibility when you have good componentization.
Yeah, so that's sort of.
Yeah, no, that's good. No, yeah, you're thinking along the right lines. Okay. So anybody else want to define separation of concerns a little bit more precisely so that we can maybe, say that increment and decrement are the same, should be in the same class, but, or maybe they shouldn't be in the same class. Maybe there's some only incremental but contours. Okay. So let me give it to you. So, like I said, Gypsy has interesting and uninteresting architectural aspects. Okay, this was the first time I was implementing an RPC system, so I couldn't certainly get it right, and I'd never seen any architecture, any paper describing what the architecture should be. And the first time you implement any kind of OO system, you don't know what you're doing. Okay, so there's all kinds of decompositions there that perhaps don't make sense. Okay, in fact, when I give you guys assignments and I realize this is what you need to extend, I go and clean up Gypsy so that it becomes more extendable. Okay? So if things work out really well for your assignment 4, it's not because I thought deeply first time, it's because I changed things. Okay? And in fact, the guys who wrote the Design Patterns book, how many of you have seen the Design Patterns book or heard about it? Yeah, GAM. So Ralph Johnson was a professor at Illinois, And I was a professor at Purdue, so I actually got to learn from him directly some of the things he wrote in the book later. And he always said, and that's something that people take as gospel now, that the first time you do any kind of piece of code, write it down, figure out what you really want, and start from scratch. Okay, that's the right way to do things. And at that point, you have the design patterns. You know what should happen. And when it comes to compilers, we all know how compilers should go, so it's easy. Whereas when it comes to something like a distributed RPC system, it's not well documented and no. So there's those that can be justified through accepted principles, and those that can't be justified. So we're interested in the ones that are justified through accepted principles, and the separation of concerns. And my reading of it, my understanding of it, says that if there's a logical component A that can be used both with logical component B and B prime, okay, and you can think of these three logical components, you can think that these are things that you would want in an application, then make A, B, and B prime three different classes. Okay? So in a counter example, if we can imagine only an incrementable counter, make that a class, then you could create another subclass that is decrementable counter also. Okay? But if you can't imagine an incrementable only class, then why bother? Okay? I mean, all these principles have a cost. You can go and give these principles and say, you're sinning if you don't follow these principles. But the fact is that we all have deadlines, and we have priorities, and we might have to trade off efficiency for software engineering principle. And a lot of people, especially in companies, they've got to worry about this next quarter. So they have to worry about getting things working rather than thinking long term, which is what these architectural principles require you to think. Okay? And so, or if I've built some system and I've given you an assignment and suddenly my software is not working, at that point I've got to make sure that the software works before the deadline rather than it's well architected, and I'll do a lot of hacks to do that, make that happen, right? So given that separation comes with a cost, okay, this is the principle to follow, that if you can imagine a B and B prime in some realistic application that will work both with A, then make them three different components. Okay? In the project that you're doing that requires B and B prime, you'll be better off. Okay? So that's the principle. And can you sort of, so that's just saying, okay, I've broken up my code into these classes that interact with each other. Can you think of even a breakup that has more modularity? And there's more modularity when there's less connections between classes. Okay, so there's one thing to go and break up your code into classes. The other thing is to go and reduce the coupling among classes. So can you think of some other architectural principle that you might have seen, that you also have seen, that says, that gives you a way to reduce coupling? Inheritance reduces coupling because
so if A works with both B and B prime, you can just have like an interface from abstract class A that both B and B prime inherit from.
That B and B prime inherit from, B and B prime being classes.
Yeah.
So this inheritance, what is the opposite of inheritance? What is the dual of inheritance that you might remember from my class, but you guys might have heard in other contexts? If you want reusability and you don't have inheritance, or you shouldn't use inheritance, what's the alternative? Polymorphism is something that inheritance gives you, Jacob.
Has a?
Delegation has a. So actually delegation gives you far more flexibility than inheritance. But inheritance does say something, even delegation says the same thing, that class, if B is a subclass of A, or if B delegates to A, B can see A, right? Can A see B? Especially if you're talking of inheritance. So inheritance is something that comes around in object-oriented languages. If you didn't have object-oriented languages and you wanted reduced coupling, what term might you use for this kind of reducing? I've told you how one can reduce dependencies. That one module sees another module, the other module doesn't see. A sees B, but B doesn't see A. What's going on here? What's the general concept here? That anonymous call.
So when you say like A sees B, but like when
Exactly. Perfect. Perfect.
That is not what that.
So when the dependency is one way,
Like a tree, let's do trees,
tree is good. Tree is good, but yeah. Indirection. Why do you think indirection? Because indirection is a good. By the way, whenever somebody asks you a systems question, just say indirection. It'll be an answer to the question for sure. Okay. There might be indirection by what I'm talking about, because you're going. When we come to the answer, I'll talk about why that might be the case. So when you think of, lots of you guys did networking, right? Think of a software engineering principle employed in networking. When you studied networking, what all did you study?
You're talking about like the network stack, each subsystem layer.
What did you just say?
Layers.
Say that again. Layering. Okay, so when A can see B and B can't see A, which is a higher level layer, which is a lower level layer?
Well, I guess depends on
Yeah, when I say higher level, I mean higher abstraction. A is higher than B. So what we've done is we made the dependencies one way rather than two ways. Okay, that's layering. And inheritance gives you one way to get layering. Okay, if a bunch of classes in one layer inherit from a bunch of classes in the other layer, then they are higher level. And they could be delegating too, and they will still be higher level layer. They may be just C routines that just call the API lower API. It might be a client calling a server, layering. Okay, so the stronger architectural principle is range component and layers. Okay, and so that's the layering principle, that you have layered and in my case, it goes opposite to the stack. So you call down, the higher level abstraction is higher, and layer I can see the API of layer I minus 1. That's the point. Okay, it sees the API of that layer, whether it sees it via inheritance or just through libraries, and maybe even lower level. So there's some debate there whether you should be going, whether layer n should be seeing layer n minus 2 or not. Okay, but layer I cannot see the API of layer I plus 1. Does that mean that layer I cannot make calls in layer I plus 1? Could be a callback. Okay, so what's the technical definition of callback then? I mean, if what's a litmus test then? I mean, can I go and look at a piece of code and say what the layers are objectively? One way to do that is to look at the calls and say the calls are going this way, so the layers are this way. But if I have callbacks also, then they're also called. So is there a way to figure out whether something is a callback or a call? If I know the layers, I can say that's a callback, but I'm trying to figure out what the layers are. So I need something that's independent of Matt.
I mean, presumably there should be more calls than callbacks. So you could look at,
So that's interesting. So you say, okay, let me figure out, let me go and try out and say, so you've got a jumbled bunch of classes. So you have to do some exhaustive search here. Let me try this subset here, let me try this subset here, and there are layers if there's more calls than callbacks. That's like a greedy algorithm. By the way, a lot of algorithms right now work that way. That could be one way. John, what are you going to say?
I was basically going to say the same thing. You can't have a callback unless you have a call first.
Oh, that's interesting. So you can't have a callback unless you have a call first. So you have to somehow figure out in what order the calls will occur by looking at the code. And can we write a program that can determine in what order the calls will occur? Sorry? Trace will tell you for certain inputs. If I want to have a general, if I just want to do it for all inputs, which could be possibly infinite,
Do you mean have a program that will tell you all the different ways a program can run, or if you run a program, it will tell you how they have been done?
Well, I want in this specific case to know that will this method always be called and after this method is called?
Okay.
Always. That's what. Why not?
Halting problem?
It's probably as hard as the halting problem, if not harder. Okay? You just can't do, halting problem says you can't analyze loops. Okay? And if you can't analyze loops, you can't answer these questions.
Just as an heuristic, if you think of a callback as always being a function that's passed as an argument to another function.
So you're saying a callback might be might be something that that is a function that's an argument to another function. In C, that would be the case, but in Java, you don't really, you can do callbacks without that. So the observer pattern is an example of callback. So, anybody else? Let's talk about the signature of the callback. Who defined the signature of the callback? Module B is calling a callback in module A. Who defined the signature of the callback? Module B or module A? B. When A makes a call in B, who defined the signature of the call? Again, it's B. A is making, I changed the modules, I'm sorry. So when you make a call, the question is, what was the API? Who defined the API? And so layer I makes up calls in layer I plus 1. Yes, because we are starting layering from here. But the up call signature is defined by I plus 1 or I? What did John say? I plus 1. Brennan came just in time to hear that answer. Right? So why is that important? Why is it important that layer I plus 1 have defined the signature? Sorry, did I get this right here? I'm starting from here, right? You can make an up call to here. Sorry, no, hang on. You guys were right in the beginning. I got confused myself. So yeah, we're making up call, right? So again, now let's reset it. So who defined the signature again? Callback signature. Lower one, layer I. Okay. So basically, that means that I should have numbered. I should have numbered it from layer 0 to n, right? Yeah, I don't know. That's the higher level layer, but I'm getting confused by my numbering myself. So the basic point is that the higher level layer sees the API of the lower level layer and not the other way around. Okay? If the lower level layer if the signature was defined by the higher level layer, then the lower level layer would know the API of the higher level layer, and you don't want that to happen. Okay? That is the litmus test. Where is the signature defined? Where is the interface defined? Okay? And typically in the observer pattern, the lower level layer can work just fine without the higher level layer. It's just notifying, saying, hey, just in case you want to know or do something else, do this. I can work just fine. Whereas when the higher level layer makes a call in the lower level layer, it typically needs some functionality. Okay, that's why notification is as a callback, a call is not a callback. Now, it may be the case that the lower level layer needs some functionality on the higher level layer also. Okay, who knows? It can do anything there. But the point is the signature was defined by the lower level layer. That is the key. Okay. So, yeah. Any questions? Okay, so that we understand layering properly, in networking, what were the layers you might have seen? Applications are top, good. Transport layer is below the application. What is the transport layer exactly?
That's TCP.
Okay. So, okay, and what else? What other layers are there?
The networking layer, which is below the transport layer, and that's IP.
That's IP. Okay, you see, he's taking the course this semester, so he really knows it. Everybody else has forgotten the stuff. You know, the finals is the point at which you know the, pre-finals is when you know the most, and post-finals is when you've purged your head and said, okay, I'm ready now to learn something new. So that's, sorry? The link and physical layers, okay? So are you studying 7 layers, the ISO model? Do you study that in your networking class?
We're doing the 5 layers.
5 layers, huh? And who invented the 5 layers?
5.
Okay.
It's just the 7 layers, except they said you can bundle the security layer and the other layer into the application layer if the application needs it.
Okay. So I told you I was a faculty member at Purdue, and in fact, my advisor at Madison and a guy called Doug Comer at Purdue together did a lot of networking work. They did the basis of what is ARPANET. And Doug Comer has written a lot of books on networking and operating systems. He, in fact, did Xenu, the system that I talked about. And he was very, you know, he just didn't like the ISO model. He didn't like the 7-layer model. And he says, yes, that's what these Europeans came up with in committees. And let's talk about the model that really works. And that was a really big deal for him. So I've been brainwashed by him a lot. So there's the physical layer. There's the internetworking layer. So, and there's link layers too. I mean, but this was the kind of layers that he focused on. So what's the difference between internetworking layer and the physical layer? IP and physical layer?
Physicals between 2 devices and internetworking is between a collection of devices.
So if I have an Ethernet with 10 devices running around here, is that physical layer or is that internetworking? So you said, you know, when it's two computers, it's physical. When it's multiple computers, it's internetworking.
I mean, well, it depends how they're connected. So I guess internetworking would have at least one middleman. So you'd have at least 2 independent wires. You could still have one wire that gets split to multiple devices. But with networking, you have a middleman that's actually doing processing for you.
Okay, so internetworking, there's a middleman. Why do you need the middleman? Well, the interpretation will ultimately be done by the application. Ultimately.
Like one message comes, you want to priority to say it is incorrect procedure.
So if a message comes in, you have to route to this right. No, that will come to the next layer.
I never took that one. I'm just guessing.
Come on, guys. This is Brennan. Have you had the midterm? Have you not had the midterm? You haven't had the finalists yet. You're not allowed to forget things.
We are on the layer above. We're focusing on the transport layer right now. I can tell you anything you want about TCP.
No, but how does, supposing I have an Ethernet here, and at home you've got a network too, right? How do, and so you've got, in your home, you don't need the internet, right? So you don't need a middleman. Because the physical layer is providing a way to send messages across. It's only when you have 2 different physical layers that need to be bridged that you get into internetworking. That is why you need a middleman who is on both networks. And so when you were talking of, I'm getting wrong IP address, I'm saying, well, every host, you can have multiple IP addresses in each host, for each host. Because IP address is network centric. It has one component as being network. So if you're on 2 different networks, you have 2 different IP addresses. Okay? So those are these middlemen. So internetworking is basically taking a bunch of physical networks and connecting them together. And you just chain them up and you can go from any network to another network using indirection, right? So so that's internetworking. And now what is the transport layer is what I guess I've forgotten the term for it. So I called it port-based communication. So why am I calling it port-based communication? Nick, what were you saying before when you were guessing what internetworking is?
So routing thing, like messages come in, you want to route to say what I said was that you want to route is correct procedure.
So you might have internetworking is host to host. right? Regardless of where the host is. Port-based communication is host to port, saying that, you know, in a host, you'll probably have multiple processes, but networking layer, it's not the OS layer. It doesn't know what a process is. It can't go and locate a process. So it says, okay, we will just assume there are ports, and we will go and make sure that we allow a port number to be put in the message, so that whoever is going to interpret that, that's the interpretation somebody was talking about, can go and figure out which queue. So it's a mailbox. It's multiple mailboxes, and you can put the mailbox in there. Okay. So these are three layers. Whether you need link layer. Link layer is between. You know, it doesn't make sense in an Ethernet, right? It's between an access point and maybe something else. So that becomes a link layer. So link layer is a little bit more specialized. And when the ISO model was being created, you know, they were thinking of all of these things. So how it goes in, and I've been in part of these committees, there is these, Europeans come up with this, IFIP committees, which they take the experts in some area, and then they all meet twice a year perhaps, and come up with some kind of reference model. And the nice thing is that most of them are held in Europe. And if you're an American who wants to see Europe, you attend these meetings and you see all of Europe. So that's, sorry? A lot of these things come from there. You know, a lot of reference models come from there. I don't know whether the ISO model came from there or not, but that's sort of the model that it's called the IFIP model. So, you know, that's sort of very, you know, and it's a very thoughtful process. And people argue, and Dave always argued, this is what works. Okay, that's what's hypothesized. You know, so, and he was very adamant about this stuff. It was a big deal to him. So, so anyway, these are at least three layers that you can talk about. Whether you need other layers or not, other layers means more indirection. Indirection is always good. Okay, so you can argue that there should be more layers. But the point is that A, you understand layering, okay, and B, this layering is relevant to distributed systems, right? How is this relevant to distributed systems? Distributed systems compared to networking systems, what are they? The layers on top of this port-based communication, distributed systems. Okay, so we need to understand what's below us. Just like in the compiler class, we need to understand assembly language, right? So relevance to RPC, that's the relevance to RPC. Okay, so yeah, distributed systems and RPC in particular. Okay, just to make sure we understand layering. Those of you who did OS and did not do networking may have been feeling a little lost in the previous slide, so I'll give you guys a chance to show what you've forgotten. How would you arrange, so you understand what these things are doing: memory management, allocation of memory, deallocation of memory, process management, scheduling of processes, creating of processes, interprocess communication, send, receive, and file management, open file, close file. How would you break these? How would you arrange these guys into layers? Let's talk of the dependency. Let's understand whether let's see whether you understand the separation of concerns principle. So let's take pairwise thing. Process management and interprocess communication, which is higher level? Interprocess is higher because?
You need to, like you want to call a process to kill or just spend whatever, but that's in process management.
Yeah, so interprocess by definition, it says once you have process, we're building interprocess communication. If you don't have processes, there's nothing to block, for instance. Okay? So interprocess communication goes above process management. How about process management and memory management? Sorry.
I mean, memory management is pretty low level because when you say like create a new process, the memory management then has to allocate the memory for that.
When you create a new process, you might want to allocate some memory for it. You might want to allocate a stack for it, right? So process management over memory management, interprocess communication over process management. How about file management and process management?
I guess like in file management, when you try to open a file, a new process is created to do that.
When you open a file, a process is created.
Never mind.
Process accesses files.
Yeah.
So files goes below or above? Process with open files, that is true. Process does everything, right? So by that definition, process management, remember, is scheduling. And does scheduling have to worry about file management? Does creation of a process, a context block, have to worry about file management? When you read a file, what happens? When you read something, what happens to the process? Maybe it blocks. That means the read routine has to block the process. Maybe it has to know what process management at that point then. Interprocess communication and file management.
It's like in pipes, for example, that's multiple processes built on top of files.
That's an interesting point. That's when you do interprocess communication of that kind, you can say it's built on top of files. Very good point. But maybe files and interprocess are built on top of notion of some common abstraction. Yes, in Unix they say everything is a file. That just means there's an abstraction. There's an API, there's an interface defined very low level that can be used both by interprocess communication and file management. But that's a very good point, that you can argue that interprocess communication is built on top of file management, if you assume that the file management is the one that defined that layer. Right? So it becomes a little tricky. Think distributed file management.
That would be like your file management would have to go on a higher level.
That means file management has to go above interprocess communication. So sometimes there's a logical unit, file management, that has to be split into two physical components to make it fit into this layering principle. Imagine a memory management routine that will block the process till the memory is allocated. That memory management would be higher than the process management. So, separation of concerns, very easy to say, hard to follow or even understand what it means. Layering, very easy to say. You start doing things and you get into trouble. I mean, and you have to think in blocks, okay? So here's one layering, where what I've done is I've gone and put I've put file management on par with interprocess communication, but I like Sam's point that maybe the file management layer provided that interface. Okay, it's really the interface that has multiple implementations, and the implementations are not layered, but the interface is common. So, but this is what you might end up doing, for instance. Okay, and again, does this have any relevance to distributed systems? We are essentially doing interprocess communication. And a lot of distributed systems were created for distributed files management. Okay? So when people build APIs, they have some driving problem in mind, right? And these APIs were created by OS and programming language people. And they couldn't think of, sequencing the genome. They couldn't think of other things. They could think of building operating systems themselves. And the big problem in distributed operating systems was distributed file systems. And that was the motivation. A lot of the IPC mechanisms were motivated to create by the IPCs. You know how when you guys studied semaphores and monitors, there was a Dunning-Philosopher problem that you all, readers-writers problem, that everybody sort of uses as canonical example. For distributed systems, the canonical example was file systems. Okay? So, you judge often how good your interprocess communication is by how flexible or how efficient a file management system you can create. And the point is that you need process management underneath you. That's why threads were so important. Threads are so important in distributed systems, right? And so, yeah. So this is not, okay? And by the way, that is the picture that you would see in PC and Unix, okay? This is what research systems were doing. They were saying the local file management should also be above interprocess communication. What would that mean?
So like the implementation of the read might use some sort of API in the layer of process communication.
And and it'll send the message to whom?
To even lower.
So like the file manager basically sends to multiple processes, something like that.
But that file manager does handle multiple processes, right?
It seems to me like the file manager would be sort of implemented as sending a message from one place to another instead of.
Yeah, so that's what it's implying. That file management requires a message from one place to the other. And normally the file manager is in the kernel. And in this case, the file manager would be outside the kernel as a separate process, as a daemon process, as a server process. This is the big battle that's going on in operating. So people have tried to put it in, put it out. You put it in, it becomes more efficient, less flexible. You put it out, it becomes less efficient, less efficient but more flexible. And then distributed file system and a local file system become the same thing. It just goes to another machine. So a lot of research systems. I was at Madison. We built one where the file management was outside. The one that really became popular, and we at Madison were a little mad because Mark got all the publicity. It was on a CMU. So Mark was a system that had a Unix-like layer, so that was the good thing. That's why it became popular. And Mark, how many of you have heard of Mark operating system? In what context? It's a microkernel. Microkernel means that the kernel is smaller than it would be normally. Microkernel is a kernel that just has, do you know what a microkernel is?
Tries to as much into the users.
Possible. And what goes in the kernel, microkernel itself then?
It's like memory management process.
And some,
Schedule.
yeah, that's process management. And from this point of view, why this course is so important? IPC. How do you talk to a server if you don't have IPC? Okay, and at one time at least, and I think even now, Mac OS is built on top of Mark. Okay, so this is not just a pure non-commercial system. So I think it still is, but it may not be. Who knows what's going on at this point? But Mark is something that Apple did adopt at one point. So relevance to IPC. Again, we are building intercommunication. And just to make sure that we understand layering well, in compilers, what are the layers? Nick, have you forgot? You're the one taking compilers?
It's like, I don't know how.
Yes, Matt?
Do you know how to
I mean, so you take the code, you do the syntactic analysis, you get an abstract syntax tree,
Yes.
and then you do that, connect all the references together.
Yeah. Good. And what do you do to the syntax tree? What do you do with the syntax tree?
generate by code?
Generate code.
Some of that.
And before you generate the syntax tree, what step do you go through?
Next in class.
Okay. So scanner,
I'm just gonna get-
parser, code generation. Okay. And so you got layers there. Now this is not that related to, well, it's kind of related to RPC because we deal with languages and we have to compile proxies, but just to sort of make sure that we understand layering, right? So relevance to RPC, I think not that much. Okay. So let's go and see. Layering follows the separation of concerns principle. So let's go and figure out, what are the advantages of layering and what are the advantages of separation of concerns in general and layering in particular. Why is layering so important? At least, and think of both an industrial environment and an academic environment. Right?
I mean, it lets you make things into components that you can get them working first, and then, if you have an outsider who is like specialized in one of the components, they can come in, fix what they need to fix, and not touch your components at all.
So you said two things. One thing applies to separation of concerns. That if I have multiple things implementing different logical things being split apart, then an expert in that logical thing can change only one physical thing. It doesn't have to go and change other physical things. That's one thing you said. You said something else before that was even more interesting. So you said an expert can come in, and you said you can build.
You can swap like components in and out.
You can swap things in and out. That's good. You can customize things. That's again good with separation of concerns and layering. But Matt said two things, and he's already forgotten it. And anybody else know what two things he said? Two independent things? Yeah.
Independent people can work on individual pieces.
That's what he said second, right? He said something first before that.
That maybe you can build things that bottom up.
You can build things incrementally.
Yeah.
You guys are doing that in compilers, right?
Kind of, yeah.
You know, you don't have to go and say, okay, go build the compiler. You say, go build the scanner, go build the, you know, gradually, right? So we've got most. Anything else? Yeah.
What I think is that, like, when we try, like, this goes back to the compiler assignment, when we're doing, like, when we're designing things, we kind of, if we have that layer, we can go top down in terms of designing, and build bottom up back again. So, you know, we go from top to bottom in design, and we basically map out what each component is supposed to do, and then we'll build it bottom up.
Okay, so that you build up a whole architecture,
Yeah.
top down, and then you implement the architecture incrementally,
Exactly.
and you can build bottom up the architecture, which is great, right?
All top down. We just have-
So can you think of this also being, supposing you didn't have supposing, how would you build it top down? Actually,
I think it's like that's.
I would just like pretend the you know,
oh, that's good. You know, just pretend that it works at the lower one.
build it down to
Yeah.
like the smallest piece that will have to resolve the problem and then resolve it there.
Yeah, there's middle out programming. You know, in general, that's the real programming. You know, you don't just build an architecture and don't change it ever. You build an architecture, in compilers you do, in Unix you do, you know, because you understand what's going on. But generally you build the architecture, you start building, then you change the architecture, then you start implementing it again, and that's kind of the typical cycle. But supposing your compiler class did not have any implementation. Okay, you just had exams and you were understanding concepts. Would layering be important then?
Still make it a little easier to understand.
Easier to understand. You explain one thing at a time. Right? So I think we've got all the reasons. You can explain, understand incrementally, can implement incrementally, can bootstrap off lower layers. Okay? So that's one of the good things, that when you break things into layers, you might realize that, oh, I already have this function. Let me go and put this function in this lower layer so they can be shared by multiple layers on top. Okay, so you can do that. And you might actually say, you know what, I built this compiler and I've got the scanner and I've got the parser and I've got the code generation. That was all to do code generation. But you know, the scanner in its own right may be useful. The parser may be useful in its own right. I might want to go and compare two programs and see whether they are copies of each other or not. And I can't do, because the halting problem prevents me from really doing a code-to-code comparison, but maybe I can do a syntax tree comparison, maybe I can do a lexical comparison. I can probably use the intermediate layers also, you know, in their own right, as abstractions, as programming abstractions. Okay, and can replace layers. So now we finally come to RPC. Okay, we understand layering, and let's go and see layering in RPC in general and RPC in certain implementations in particular. So the classical way to implement RPC, okay, and one of the first RPCs that were Unix oriented, you know, RPC got invented in CMU, got implemented in CMU, MIT, a lot of places before Sun RPC, but Sun RPC was an RPC system built for Unix and C. But the general architecture was that you have byte communication layer, okay, and you build on top of that an RPC system. Okay, and in the case of Sun RPC, the byte communication layer was sockets. So Sun RPC was the first layer I know that was implemented on top of sockets. How could we, now that we understand layering deeply, can we imagine at least one more layer here. So the question is, what kind of layer might go between byte communication and RPC?
To translate the byte communication into something more meaningful, so I guess you might have a layer that changes those bytes into objects, and then RPC sits on top of those objects.
Object communication over byte communication and RPC over objects. And does Java provide that, RMI? Or Java in general? Forget Gypsy.
Like serialization and marshal there?
So serialization and then RPC. So the big innovation as far as I'm concerned. Okay, by the way, with this layering, this was great. Sun RPC was built. There were socket layers implemented on all kinds of operating systems. And Sun RPC would work with all of these operating systems. So you could replace a socket layer with another socket layer. You could not replace a socket, you can't replace, so that was good, okay? You saw this advantage of layering, okay? And can we do better? And Java did that, okay? It provided object communication in between, and a lot of people use object communication only. They don't use RPC, okay? Because RPC has an overhead, and they will just use, in Java, you can take an input stream and convert that to an object input stream, in general, okay? And that involves serialization. So you just took the input stream from a socket, converted that into an object input stream, and that part was, on top of that was layered the RMI. Yeah. Okay? So object communication often used directly as an abstraction, which is what I was trying to point out. But you can't replace sockets with an IO in this layer. Okay? So we might want to do better than that. And that's where Gypsy comes in. So, and what's the key there? You just need some layer to unite the byte communication layers. Okay, some interface, and you just map it in direction. Okay, always to the rescue. So we just provide another layer, and this is sort of the and in Gypsy, each layer is a port. Okay. So you have and this is something that you'll see in your implementation. There's a buffer port, there's an object port, there's an RPC port. Okay? So the RPC port and the buffer port is built on top of sockets and IO, other things, and you need to essentially have a driver for each of these layers and do that. So the Gypsy implementation you have is just NIO, but when I've taught this course to grad students, I've had them replace the NIO layer with a socket layer because they hadn't done socket programming, so I figured they would benefit from that. You guys have an undergrad course that focuses on that, so I didn't want that to be a project. But you can actually do that. You can take the Gypsy layer and NIO layer and replace that with socket layer, and it'll all work on top. And then you have the object communication and RPC communication. Okay? So this is something you need to be aware of for your project, and it's also interesting from an intellectual point of view. Okay? So there's a channel mechanism that delivers and receives messages on the network, and that's sort of the socket and IO other layers. Okay, and you can choose the driver. So the issue is layer visibility. I said that when you design a layered system, you have to figure out how deep do you allow layers to see. So So the question for me was that when you're working at the RPC layer, should you be able to use also the object layer and the byte layer? And before we figure out whether you should or not, what would that really mean? So you're doing the RPC, which means you've got proxies and you're making method calls on proxies. You don't even see any ports as such. So what would it really mean to sort of see the layers underneath? I mean, I can always go and just use the object layer directly without the RPC layer, as in RMI. That's fine. No problems there. I'm saying I am using the RPC layer. I have got an RPC port. Okay, and I want to use also the object and lower level layers underneath. What would that really mean? Okay, so that's interesting. What you're saying is that you can do some customization, which means you can somehow intercept the messages that are going underneath.
Yeah, you can change the default behavior.
Okay, right. You can change the default behavior to how messages, because underneath we know the RPC layer is sending messages. So maybe we can go and intercept those messages and do some optimization, and that's exactly what you'll be doing in assignment 4. Okay? So you asked for it, you know. You said we can do it, and I said, okay, you know, I'll let you guys do it if you really want to. So, but actually that's not what I was talking about. That's customization. I'm saying layer visibility. That in the application layer, if you're doing the customization, you're working at lower layers. I'm saying you're working at the application layer and still using the lower level layers. Sam, you were going to say something?
I was just going to say that you could change blocking.
Yeah, yeah. So we've got a process that's sending call messages and getting return values, right? We know underneath these messages are going across. And what you guys are saying is, let's intercept them, let's do some optimization, or let's slow things down, let's maybe timestamp messages, yeah.
Looking at this picture, like, if you want to, like, if you ever want to see what's happening on lower layers at application level, is maybe, like, something goes wrong, and you want to see, like, which layer is causing the issue.
Okay, so you're not just doing customization, you're just doing, you know, you're trying to debug, right? Yeah, so that's, okay, that's something else you could do. Sam?
Maybe if you want to make threads or something like that, like you're going to get a return or whatever, and you want to have return messages coalesce somewhere, and you want to intercept them as soon as they came in and delegate it to another process or something like that.
So you're saying that you want to do the return values and delegate and to another process. Why do you want to do that?
Just maybe, like in the case that we were building RPC on top of our communication, maybe you want to take the message, like you get a move command or something like that, maybe you want to pass it to another thread the way NIO does, and let that thread work on it separately from you.
So are you trying to customize, or are you trying to go in, are you trying, because,
In some sense, yes, I'm trying to customize, but
or maybe you want to just add some more functionality to your application.
yeah, in some sense you could get some efficiency, I guess, if you were able to take everything that was returned to you and, you know, put that in a thread somewhere else that might, you know, keep you on track and give you.
So what you're saying is that I don't want to change, so what do we do with these messages? One answer is we change them. One answer is we go and figure out what's happening. And in your case, you're saying we'll do some extra processing.
Yeah, you know, we're able to almost put a layer on top of that, almost create, so if you are aware of your bottommost layer, you can almost create a layer in between that doesn't exist.
And then what happens to the RPC message that went to the person who's waiting for that call? Do they not process it now?
Yeah, they can be non-blocking, I guess, in some sense, or just not, you know, worry about it.
So it's getting a little messy there, right? Why did this make an RPC call in the first place?
Then you basically rewire the entire.
I didn't say it was pretty.
So,
Yeah.
okay. So we have 2 minutes left. Let me at least complete this picture. We know there's underneath a buffer channel. We know underneath there's an object channel. Maybe we make some calls via RPC. Okay, maybe we make all these consensus calls via RPC. And maybe we send some communication using objects. Object communication is kind of what you're saying. And maybe we send some buffers too. We know this stuff is we need to send byte buffers for some reason. Okay, and we send that too. So we are sending mixed kinds of messages there. Okay, RPC messages that are sent internally and our own messages, and that makes the RPC implementation more complex because we've got all this communication happening. Okay, so whether this is a great idea or not, I don't know, but I could do this, and I can imagine situations like you're talking about where you're saying that the same application, we've seen there's trade-offs in different abstractions. And there's no reason why a single application might not have multiple kinds of needs, and why they should go and open up multiple message boxes. Why not just have one message box with one port being used for all of these things? Okay, so that is what's going on in Gypsy, and that makes the design a little bit more complicated. So what really happens is that the proxy calls are all going through an RPC port. Okay? And the RPC port is built on top of an object port, which is built on top of a buffer port. And you can go and find out, you know, when you're using an RPC system, you can find out what the RPC port is, and then use the RPC port to send both object messages and buffer messages. Okay? So that's kind of an important point, and I'll leave you guys at this with this slide, and that's sufficient for you guys to understand what's going on, you know, to a large extent in assignment 4. Okay? Yeah, Sam.
So is that saying basically you get the efficiency of a byte message?
Yes. So when you send byte message, you're not going through the serialization layer. Yeah, and that is, by the way, very expensive. Okay. Okay. So, and by the way, the RPC port is an object port, is a buffer port at the interface level. At the implementation level, they use delegation. But the interface level, the interface of RPC port is a object port, is a, okay? Okay. Okay, so what we were doing last time was looking at the concept of layering in general. Okay, and we saw what layering gives you in general. We took some examples that are familiar to you from other domains like networking. Networking is where layering makes the biggest point. If you ask a systems person where's layering, they'll say networking. They won't say often operating systems because people haven't thought about that very carefully. But we looked at operating systems and we saw how layering could work there. So that helped us understand layering better, and also helped us understand the particular component of operating system interprocess communication in which we are interested a little bit better, how it's placed. Okay. Then we just to make the point clearer, we looked at compiler layers, and then we started looking at distributed systems in general, and we saw that you can have a two-layer system as an original systems where the RPC layer is built right on top of the buffer layer. Then we saw in Java RMI that there is in between an object layer. And then we looked at Gypsy, which was meant to be customized. Okay? So if it's meant to be customized, it should do a little better job than the previous works. And it does do a more fine-grained job. So as in RMI, we have an RPC layer on top of an object communication layer. And the object communication layer is not built directly on top of a particular byte buffer layer. It's built on something that virtualizes the layers below it, which is a driver layer I'm talking about. And those layers are then built on top of specific byte communication mechanisms. Okay, so it could be sockets, it could be NIO. By the way, if you go to industry, what is the mechanism that you're likely to use for communication, for remote procedure call? What is going to be the transport mechanism that you expect? Are you going to have unfettered access to sockets? Or are you going to be using something else, you think? You want your application to be used as many places as possible, behind firewalls. So what kind of applications can you, how many of you have interned in industry? So when you're behind firewalls, I'm sure you had firewalls in your company, what kind of network access were you able to use? Do you understand what, so do you understand what the goal of firewalls is? Yeah. They prevent access to some port. That's the mechanism they use. Okay, and which port do they normally use, allow? And some ports they allow, some ports they don't allow. Which is one port they always allow. So there's outgoing traffic, there's incoming traffic, right? The distributed systems that we're talking about, anybody can build a server, right? Can you build a server can you have a server running on your machine that anybody in the world can access in a company? And the answer seems to be no, the way I posed it. Why not? What are companies afraid of? So, yeah.
getting DDoS, just having tons of traffic, or even worse?
Denial of service?
Yeah.
So if you build a server, you can have denial of service, right? So that kind of traffic is always prohibited. And you're also trying to make sure that you don't go to untrusted ports. So the one port that you can't do business without is you have to allow web access. So a lot of RPC systems are built on top of web. So they're cheating. The reason why you allow web access is because web access is not supposed to, to be safe. But then what people do is they go and build RPC on top of web, and then the RPC application can do anything. Okay, so there's always this tug of war going on. People want access to services in a company, and the company says, "Oh, I'm afraid of denial of service. I'm afraid of doing dangerous things." So if you look at Google's RPC, for instance, and a lot of other RPC systems are built on top of HTTP. There's something called SOAP that's built on top of HTTP. So the reason, I had this serialization mechanism in mind, assignment in mind for you guys, and that's because you need now different kind of serialization. You're serializing over HTTP connection rather than just using RMI serialization. So that's an interesting thing. So when I say NIO socket, I could also be doing it over HTTP. Okay, I could have a little driver that sends traffic over HTTP, and then it's safe. Okay, so I wanted to make sure that this kind of system is available. So today what happens is RMI is built on top of sockets. You can't use it over HTTP. You want something over HTTP, use Google's RPC or somebody else's RPC. You use SOAP. So that's one of the reasons why there was this layering. Okay. So that's layering, and we have this channel mechanism, and we can choose the driver. The channel is the physical layer that's doing it, and the driver is intermediary and a layer, and that's terminology I was inspired by operating systems, where you try to have a driver that unites multiple physical devices. Okay. So one of the issues about layering is that once you've got layering, regardless of what layering you have, does a higher level layer expose the functionality of the lower layers? Okay, so you can build an abstraction on top. You can allow programmers to use the high level layer, or they can say, no, I want only the object communication layer, or you can say, I need the buffer layer. But what if you decide to have the RPC layer, high layer? And you say, yes, I want to have RPC traffic, but I also want to, you're built on top of these other layers, hey, please provide me with functionality that accesses those layers too. Okay? So what does that really mean? Okay, and I kind of left you guys with this question. So we have an RPC layer, that's what we're talking about, RPC. And we know that RPC underneath involves messages going to the call process and messages coming from the call process. Okay? And those messages are created by the RPC system. Okay? So we know that underneath there is an object layer being used. We can leave it at that. Or we can say, well, we'll allow also access to lower layers. And so what might that mean? So I can directly go and send my own message that is a non-RPC message, and that non-RPC message could be a byte message, or it could be an object message. Okay? Why we might need to do that, let's forget. It's more flexible. Okay? And we've seen that there are times when RPC is the right mechanism because we want remote procedure call. Sometimes we want remote assignment. The same application may want both things to be done in a distributed program. Okay? In a regular program we have assignments and procedure calls, so why not in a distributed program? You can think of it that way. Okay? And when you guys do your implementation, your assignment, you'll be essentially sending your own messages, and so you need access to that functionality also, but you'll be working at lower layers, so that's not a good enough reason. It's a good enough reason if you can do it at a much higher level, application layer also. Okay. So we know that proxy calls are processed through, so what happens, how do we do this? we expose the notion of a port. So in RPC, there's no notion of port, right? You just have proxies. There is no socket channel, no socket. There's no port as such. You never name something. Okay, that's all built underneath. But that's in Java RMI. There was Sun RPC that actually exposed the notion of a port. It did not have language support and it didn't have proxies, yet you were able to make remote procedure calls. We saw in the exam that I gave you an RPC system that had a port-like notion. You use process IDs. That was a remote procedure call. You were going and invoking a procedure call. And that exposed the notion of port. So we first go from RPC that is port unaware to a port aware RPC. Okay, so we have that idea first. And once you've got a port, and that port now is going to be an object port, which is going to be a buffer port. So we have all the functionality of the buffer port and an object port plus the RPC port also available. Okay, that's the basic idea. Okay? Questions so far? So I'm just trying to tell you how do we design an API that does all three things. Okay? And here's an example of how that's done. So this example shows you what you did in assignment 3. Okay? And in assignment 3, you have the idea of and that API was totally inspired by RMI's API, even though it's a little misleading because RMI does different things. So you have the notion of, just as in RMI, you have locate registry, I guess. So now you've got Gypsy locate registry, and you do get registry, and the difference is that you have to, I think the get registry name is pretty much similar to the one in RMI, and so this is your client. It does the get registry, and then from the registry it does a lookup. Okay, and the lookup is the one that's different. The lookup takes the class as an argument, which in RMI's case you don't have to do. Okay, so let me go and create my pointer here. Okay, so we've got this particular extra argument. Okay, and in do operations, I just make a remote procedure call. Okay, so that is the world RMI-ish. Okay, all you're doing is exposing the proxy. Now what we do is we've got a multi-layer counter client. So we've gone from the simple counter client to a multi-layer counter client. And before we do our init operation, we do a set port. And then after init, we don't just do operations, we do send byte buffers and send objects. Okay? And we've got now the set port operation here. And it says from the registry, please give me the underlying client port that you're using. Okay, so I've gone and asked for something underneath. Okay? And that port, I've gone and assigned to a duplex RPC client input port. Okay, there's also a duplex object client input port, there's a duplex buffer client input port, there's a duplex RPC server input port. Okay, so just as you have server channel and client regular channels, you have client ports and server ports, and then you have duplex versus simplex. I mean, there's a whole, I told you there's a whole design space of IPC, and the implementation of Gypsy tries to cover the whole design space. Okay, so this is what a port is. This is the kind of port that you'll be talking about. That's the higher level port. To do your receives, you'll be working with the object port that Sam was talking about, another buffer port, and there's a way to get to the object port that's being used in the client port, in the RPC port. Okay, that's extension we'll talk about. So far so good. I can get from the registry the port. Okay, from the registry I can get not only the proxy. Okay, and if I just get the proxy, I'm living in the proxy world, in the RMI world. But I can also get a port, and if I get the port, I get now into the socket and socket channel kind of world. Okay? And send byte buffer. Yeah. Let's try not to go back because I'm recording. So why don't you use your imagination?
Yeah. So like before you do operations, you had send objects.
Send objects and send byte buffers, and there was no logic there. I just was doing it. Sorry. Right here.
Oh.
Okay.
Sorry.
So, with recording, that's one of the disadvantages that you you can't go back. Now, if I used mix for doing this recording, mix will actually let me go back and it'll remember, you know, it'll give me both. But mix I can't sometimes get to work. So we see here what's happening. I mean, what's happening is not anything unexpected. I've got a port, I've got a send operation. The send operation can take a byte buffer, or you can take an object. That's what they're doing. Okay? So again, this is a nonsense application. Well, it's not a nonsense application actually. What I'm doing is I'm incrementing things, incrementing the counter remotely 3 different ways. I'm either incrementing it by doing the increment operation, or I'm sending the increment value, or I'm sending a byte buffer that represents the incremented value. Yeah.
So if we have received, like, go iteratively, like just keep on going until it can't receive anymore, would it receive like 3 different things for each time the client runs with the server?
Okay, so if you were doing your assignment number 4 and doing receives, what do you expect, by the way? What do I say in the assignment? So would you expect the receive to receive this particular receive? If
I'll say I get a byte buffer, then I get an integer, and then I get a serializable call. That's the 3 things that I get.
You don't know which each of them can trigger.
Okay, guys. So what Brennan is saying is that the receive that at the API at the client end, when you do a receive on the RPC port, right? You get all 3 things, right? And is that what and that receive is at the, is that what I specify? Or do I say that you shouldn't get the RPC receives?
I don't know if that's what I'm asking, because I get all.
Yeah, just look at the assignment, what I specified there. Okay, you can imagine that if you want to customize, you get all 3. And I think we need that for the next assignment. Okay, but yeah, you'll have to just look at the assignment to see what, because I wrote that before spring break. Okay, but you have in your receive notifier the fact that you've overridden the receive notifier. You can go and check whether you should forward that serializable thing or not. Okay, so you have the ability to go and filter out the internal messages. Okay, so just look at what I asked for, because that balances, you know, that depends on, you know, what the other assignments require and what the requirements. So I worked it out when I was writing it down, but I've forgotten by now.
And would you check that using reflection, just getting the class there?
So how do you check if what the class of an object is? Instance of. Okay, so that's kind of reflection. Okay. Okay, but that's an important point. That does the receive get the internal messages or not? And just check what I wrote there. Okay, I'm pretty sure I addressed that issue when I was writing the assignment. Okay. Okay. Questions? Okay. But we will see. What do you think? Okay, so I'm going to pose a similar question a little later. So now let's go and talk about how receive is done. So what Brennan is talking about is a receive that you guys have added to Gypsy. And what kind of receive is actually provided by Gypsy? And that's the question. And those of you who've looked at assignment 4, you know the answer. But way back, last time, Nick was telling me that he didn't like the receives that current systems provide. And what kind of receive did you want? You mentioned something. It's always interesting.
What was the information?
So you were talking of the observer pattern last time. And you said you wished receive was built on an observer pattern.
Okay.
And what would it mean for receive to be built on top of the observer pattern, and why might you do it? So there is no explicit receive in Gypsy. There's only implicit receive. Okay, so we guys have seen this when we're looking at ports. There's a notion, you can always have a blocking receive, which is explicit, and that requires thread programming. And if you need to receive from multiple ports, like the server needs to receive from multiple sources, you need to somehow go and have multiple threads, each thread going in, doing a receive on a different port, and that's kind of, that's more involved. And what people have found is that thread communication, thread creation is expensive. So if you don't want that, you can have a select, as in an IO, but you guys have seen that programming select is tedious, right? And we know in RPC there is no explicit receive, but in lower level layers we've always seen that there has been explicit receive. So what Nick said last time was that he wished those things were based on some kind of listener or observer pattern. So that's exactly what Gypsy does. Gypsy by default, I put that receive stub in just to just to give you some boilerplate stuff that you don't have to duplicate. But there is no receive in Gypsy. Okay, that receive does nothing. Okay, so how do you receive things? You use the observer pattern. Okay, and so somebody want to tell me why? How if you've looked at assignment 3, 4, you know how it works to some degree. If you haven't looked at assignment 4, I'm more interested in hearing from you then. What would it mean to have used the observer pattern to do receives? First, the people who have not looked at assignment 4. Yeah.
So I guess if you have 3 different things, like listen to one sort of mechanism each. So you have 3, one for listening in the object, one for byte buffer, and one for the serialized thing. And then there's like a central receiver that subscribes to all these 3. Each one of them changes, sends a notification, wrapping the whatever message is coming around to the central receiver, and then does the processing.
Okay. So you're saying, let's look at an application that needs to receive these 3 things.
Right.
Byte buffer, an object, or a call. Okay. So remember, we have no receive statement now. We are not, I understand that in your assignment 4, we have to implement receive. Let's imagine that we are not going to have any receives. No explicit receive at all. Okay? We still want to write application programs without explicit receives. So you're kind of there, but I want to be a little bit more specific and precise. So I want to go and create an application program that can receive a serializable call if necessary, receive anything else if necessary, without having an explicit receive. So how do I get data? And the hint is we use the observer pattern. So what's the exact API?
Subscribe to 3 different ports, I guess.
So if you have 3 different ports, you subscribe to 3 different ports. If you have only 1 port, in my example, you had only 1 port. So subscribe to port means what? Just be a little bit more precise here.
Subscribe.
Subscribe to the port means that you go in.
You will be notified if something would happen, like some sort of trigger on the thing you subscribe that would broadcast it back to you.
So that's the general broadcast subscribe paradigm. Okay, observer paradigm is you register yourself as a listener for some interesting event.
Right.
And now the interesting event is?
There's 3 different.
It could be 10 different. It could be 11 different receives.
Right. Yeah.
So the interesting event is a
Message.
message coming in. Whatever the data is, whether it's going to serializable call or whatever. Okay? So, and explicit receive, we will see can be implemented on top of this. Okay? And the underlying implementation may create threads. So observer pattern is that you have observables that have registration methods like add, remove listeners. You have observers that have methods that get called, callbacks. Okay, and whenever the event occurs, that some method appropriate to that event gets called. Okay, and observers go and call the registration method. Right. So there's a down call from observer to observable. Okay, and whenever a message comes in, there's an up call from observable to the observer. And the API of the up call is decided by the lower layer. Okay, we saw that last time. Okay, so it's the observable that defines what methods it will call. Okay, So this is a paradigm, and for some reason there's been no IPC system beyond that has used it. But so I used it in Gypsy. And what am I expressing interest in? You kept talking of 3 ports, 4 ports. Of on each port we'll have a different subscription. Okay, that's what we were talking, right? We were motivating why we need implicit receive. That we will go and add ourselves as listeners to all of these ports, and whichever method gets called, the thread is now not our thread. The thread is the underlying implementation thread, and the implementation can create a separate thread for each receive, or you can create a single thread. That's up to it, and we can try to go and change that too. So the same kind of issues that arise in RPC arise now in the layers below also. Okay, that each receive could be done by a separate thread or a thread for each client. So, okay, and the event that occurs we're talking about is message received. Okay, and as Sam was mentioning, the message received takes a source name and a message here, so we can do a little discrimination and say, let's go and see which queue I want to go and look at for our assignment form. Okay, so that's what, if you weren't understanding what we were talking about before, that's what we were talking about. Okay. Question?
So this is kind of going back to 4, to my question I asked before. So message received is the callback for when you get a message.
Yes.
But so is that not where we're supposed to handle the producer adding to the queue? Is that then going to call our custom notifiers somewhere else?
So I'll talk about what the relationship between notifier. Right now we are not seeing the notifier. Notifier is an internal block in Gypsy. Okay. As it turns out, for assignment 4, there was a reason that I wanted you guys to work at the notifier level and not at the listener level. And I think the reason was what kind of Nick alluded to when he was talking about a central thing, that I want a listener is just one of these. If you're a listener, then you become one of the listeners. And what I wanted, I think, done was that I wanted a central guy. The notifier is a central guy, and I wanted some kind of customization there. And that can go and then call the listeners. Okay, so we'll look at that listener and notifier architecture a little later. But there was a reason why I thought that would be the good idea. Okay, rather than being one of the listeners, you are the notifier. Okay, and that certainly gives you more control. Okay, yeah.
I guess the reason I talk about a centralized thing is basically you get to put all of your processing for incoming message at one place. So it'll be easier to see, like, this is all the processing I'm doing to incoming messages, instead of I'm doing incoming messages for objects here, for serialized stuff over there, like in different places. But, that's the reason I say centralized.
Okay, so you were mentioning centralized because you were thinking customization.
No, I guess it just means like all the processing stuff are together instead of sort of scattered across the code base.
Yeah.
I don't know if that is a good reason to use it.
Okay, so you have to make up your mind whether you're talking of the application programmer or the guy who's going to extend Gypsy. If you're talking about the application programmer, in general, putting all processing, the increment operation and putting the decrement operation and everything into one piece of code is not a good idea, right?
No.
Right? So the application should have multiple listeners depending on what kind of message we're talking about, what port we're talking about, right? But the central thing allows you to intercept every message.
Right.
So if you're going to, for instance, timestamp a message and then untimestamp a message, you want to see every message. Okay? And that is where you will put things in the notifier rather than in one of the listeners, because you want the message before it goes to any notifier. Okay? Now I forget in your assignment whether you need to massage or intercept every message that goes to a listener or not. If you're one of the listeners, you can't do that. If you are in the notifier, you can do. You have more flexibility. Okay? So again, I've kind of forgotten, and if you want to, for instance, take out the serializable call message, okay? You can do it at the notifier level. But if you but if you do that, maybe the RPC system built on top of that will not work, right? So that's the challenge. Okay, but at least you understand how the receive notifier works. So now we are getting closer to how to implement assignment 4. Okay, you know that you've got to implement explicit receive, and you have to use this particular underlying mechanism. Okay, and like I said, when we study IPC, there's always this duality issue that can you use one IPC mechanism to implement another IPC mechanism, and the reason I like assignment 2 is that you're doing exactly that. They're both at the same level, and then assignment 2 point, the part 1, part 2, and 3, you're building a higher level abstraction. So input port may be bound to different message types. That's why message type is a generic. Okay. So the source name, you know how in, you've got this message that's arising, and you've got, you're receiving messages. If you're a server, you're receiving, you can't go in with this mechanism. You don't say receive from this particular source. Okay, we don't have that flexibility now. So so you'll have to go and look at the source name and do different things depending on different people. So that's perhaps a disadvantage of this mechanism. Okay, and that's perhaps why sockets and socket channels never implemented this mechanism, because socket channels were meant to create duplex ports. Okay, and here I've got an input port, even so that's one disadvantage of using the observer pattern. Okay, so here you have to do your own demultiplexing and go and say, okay, I'll handle this message for this. If you have, sorry. Well, it's a free port when we talk of a particular machine, but when we are talking about two different machines, then in Java, remember, it's a duplex port.
Yeah, but it's a duplex free.
Sorry.
For the socket channel.
Socket channel and socket, they're duplex port. But now I don't have a duplex port. Okay, here. Now what I can do in Gypsy is create a duplex port. I can say I'm restricting this to only 2 parties. Okay, so I told you that this is, I've got duplex, I've got simplex, I've got group. So if I want to, I can create something that's only works for 2 parties. Okay, so there's trade-offs here. Okay. Okay. And one of the nice things about this mechanism of programming is that if the sender, it's a datagram-like programming. If the sender sends this chunk of data, you get notified when the whole chunk gets received. Whereas in socket and socket channels, you get it byte at a time. Okay, you can get in your read, you can get 2 messages, or you can get half a message. Okay, because it's a stream-oriented thing. This works reliably. It works on top of TCP/IP, but you're getting exactly a unit at a time. Okay, so your programming model gets a little different. Okay, questions? Okay, and here's a real code. So this is the server now for the multi-layer server. The multi-layer server has got a method to do increments. Okay, and the multi-layer server goes and says, I want to add a receiver. So I go and get the RPC server port. Okay, so the client got from the Gypsy registry the RPC client port. This one is getting the RPC server port. Okay, server port and client ports have different APIs. Okay, just as socket channels have server socket channel and a regular socket channel. And I'm saying add receive listener, and I'm giving it the listener here. Okay, which is my multi-layer receive listener, and I give to it the counter object because I know I want to go and process the increment operation. So whenever the message 3 comes in as a byte buffer, I want to go and decode the message and call increment with that particular number. Or when number 2 arrives, I want to just take the object and call the increment operation. So I send to the multi-layer receive listener my counter object. Okay. So I did the init, I did the set port. In my original program, I just did the init. Now I did the init, I do the set port, and I add listeners. Okay, I could have multiple listeners too if I want to. Questions? And here's my listener. I take the counter, assign that to a instance variable, and when the message received method is called, I check if it's a byte buffer. If it's a byte buffer, I go and do some decoding, and I call counter.increment and I out of the decoded value. Otherwise, I go and just do counter increment on the received object value. Okay, so I have 3 different ways now to do the increment, and we see now, why RPC is a better API for this. Okay, there's more work being done at the lower layers. Okay. Questions? Yeah.
So in our case, are we going to have our receive pass it along to all the listeners?
Sorry, I receive.
Sorry, our receive, do you want us to take, after, so you put it into the blocking queue and then your receive takes it off the blocking queue. Do you want that to then pass it to the other listeners? Or like in our notify all, do you want us to put it in that block, have the receive do it and also pass to the other ones? Does that make sense?
Okay, there's 2 questions you're asking. One question is that once you use a system with explicit receive, okay, do receive listeners ever get the message or not? Right?
Yeah, exactly.
So if you have done a receive, okay, and you said receive from this client or receive in general,
Yeah.
okay, the question is, do those messages go to receive listeners or not? That's one question.
Yeah.
What do I say in the assignment?
You say they do.
Okay, good. Question answered?
Yes.
Okay, good. The second question is, how do you make that happen?
Yes.
You seem to indicate 2 alternatives.
Yeah.
One is that to do this kind of receive, you've got to go and get message from a queue, right? Right?
Yeah. Mm-hmm.
And you're saying, does that module that gets a message from the queue then send it to the receive listeners?
Yes. Yeah. Mm-hmm.
Or does the receive notifier do it?
Yeah, exactly.
What do you think?
I think it makes sense to do when you got all the queue. Because that is doing the receive in some sense.
Okay.
But
Do you have code already in Gypsy to go and send it from the receive notifier to the receive listeners? Do you have somebody maintaining that code? Is it somebody's got a list of the listeners and they're sending it already?
yeah.
You want to duplicate that code?
Yeah.
Why?
No, you don't want to do it. I guess it would just be a matter of timing. Like the mechanism would be the same. It's just whether you do it in the receive or whether you do it, say, after you add to the queue.
Oh, will the semantics be the same? Supposing somebody did no receive.
Yeah, then none of the listeners would be notified, which I guess is not what you want in some sense. Okay.
And you're also not reusing existing code.
Right.
Okay. Okay?
Yeah, but yeah, I guess I was just curious if the receive would in some sense block. Oh.
Okay. And you don't want to rely on a receive, on there being a receive to send the notifications. That should still work.
Okay.
Okay? Okay. Nick, you were asking Brennan some question here on this slide. So
No, I was just making sure that the message received, this method is defined in the interface from listener.
Yes.
Because I don't see the override sign. So.
Yeah. Everything is override in my world. Okay? All public methods have to be in interfaces. If you didn't do that, you got punished in my class in 401. And Waiting says that's good. The other students might not have said so. So, okay.
Yeah, I guess it would make sense.
Yeah. And I'll motivate interfaces even more before the end of the lecture, probably. Okay? Okay. So, we were talking of layering, okay? And we understand how Gypsy layering works. We also understand how the Gypsy receive works. We also understand how we can expose lower level layers and higher level layers. And we've seen a new form of receive, okay, which has not been used so far for object and byte buffers, so it has some pros and some cons, and maybe it's not such a great mechanism for file transfer, okay? And sockets and socket channels were created for file transfers, for FTP. That was the big driving problem. Okay, so this is maybe not the right mechanism for that, but it may be the right mechanism for building an RPC system. So let's talk about this, you know, all these things are nice. This is the nicest, right? From the point of view of learning and from the customization, we can replace things, okay? So let's talk about separation of concerns and replacement. And with this layered approach, we can, in theory, go and replace a whole layer. Okay, so I kind of motivated that and said I can replace the socket layer with the NIO layer. And like I said, I have taught a version of distributed systems for grad students in which they exactly did that, replace the NIO layer with the socket layer. But that's, you know, maybe this layer is small enough that that's doable in an assignment. But when you get to here, I don't want you guys to build a whole new RPC system. But I want you to get a flavor of doing RPC. So I might want you to replace some component of an RPC system, which means I need to componentize beyond layers. I want to be able to say something about what's going on inside a layer, okay? And that gets, you know, the finer grained you get, the more issues there are, who knows what the right answer is for these issues. So I'm going to talk about something quite generic that's not specific to this particular implementation, and that you need to understand to go and do your assignment number 4. Okay. And it's based on the notion that a higher level layer sends data through the lower level layers. Right? Objects sends it through the byte buffer. Proxy calls go through the object layer. So in terms of producer-consumer, okay, and receives occur from lower level layers to upper layers. Okay, and with this observer pattern, it makes perfect sense, right? We are making up calls up the layers. Right? If we were doing explicit receives, we would make down calls down the layers. Okay, the object layer would go and call a receive in the buffer layer, which would call a, you know, which would do a socket receive. Okay, but since we are doing listeners, they are going all through up calls. Okay, so when you're sending data, and we were talking of this before the class, what producer consumers, when you're sending data, the higher level layer is the producer, and the lower level layer is the consumer. And it goes the other way around for receives. Okay, so that's the ultimate producer, the highest layer, and the lowest level layer is the ultimate consumer. Okay, ultimate producer, ultimate consumer. Whether you're doing explicitly or implicitly, ultimately the consumer-producer relationships are going in the same direction. Okay, and what the intermediate layers are doing is creating intermediate producer-consumers. And what we'll allow to happen now in replacing is allow in between the producers and consumers, in between layers, we'll allow additional trappers. We won't go from a layer to another layer directly. We'll go through some modules that are just what I'm going to call trappers, that can trap events and forward them, and so that you can massage things without having to change a whole port. You can go and monitor traffic. Okay, sort of like what you were saying about centralized. Okay, so we will go and allow, given that we know what's happening is a producer-consumer relationship, we will just go and add, we will allow these producer-consumers to be added in between. Okay, so we'll call the things that exist between layers as trappers, and we'll allow arbitrary long chains of trappers to be interposed. And we'll also do some normal functionality through trappers also that you can replace. Okay, so for instance, when you go from the object layer to the buffer layer, the serialization is not done by the object port, not done by the buffer port. It's done by a trapper that sits in between them that does the translation. And you, if you want to change serialization, you just change the trapper. You don't change the whole port. Okay. Similarly, when you guys will be doing procedure calls, then you will not go in the call invoker and call processor. You will be trapping that. We'll see what that means, rather than trapping the serializer. Okay, so that is the key. Okay, so that's what I'm saying here. Okay, I'm saying there's layer I that's sending data to layer I+1, layer I decides to go and build a whole trapper chain. So this is layer I put these trappers in there, and then it sends data to the first object in the chain, which sends it to the next object, and finally the message goes to the ultimate destination. Okay, so we are going from layer I. So that's what's happening in the send direction. In the receive direction, we are going from layer I-1 to layer I, and the layer I-1 receive listener has to finally send the message to the layer I receive notifier, which sends it to its listeners. Okay? So it doesn't do it directly. It builds a trapper chain, and then it goes to receive notifier, and layer I will go and send it to the layer I receive listener. Okay? So layer I-1 receive listener sends it to the layer I receive notifier, which sends it to the layer I receive listener, and it goes through this trapper chain that is fixed by the lower layer. Yeah.
So in this diagram, the trapper for receive are defined by layer I-1.
In both cases, the producer of data makes the trapper chain. Okay? Because it's the one that's guiding, it's in control.
Is the order of the trappers arbitrary, or is that specified?
So it's specified, it's specified by the layer. So there is, you want serialization to be done before. So supposing this is object port, and this is a buffer port. If this trapper is a buffer trapper, buffer to buffer sender, then the serialization better occur before. Okay. So in that case, it's defined. Okay. But we have control. So it's not so easy, but basically this is notion of, I was trying to use notion of pipes at a fine grained level. Okay. And you know how in pipes you can, sometimes the order matters, sometimes the order doesn't matter. If one process is removing semicolons and the other process is removing left parens, it doesn't matter in what order you do them. But if one is doing left parens and semicolons, and one is doing semicolons, then it matters. Okay, so we can have predefined and programmer-defined trappers, and these trappers can be either proxies, which means that they just forward the same kind of traffic forward. Okay, so this we know in the web world we have web proxies that do web caching, for instance. So they are just they're not doing any translation. They're just interposing some functionality. Okay, so here a trapper could go and just put a timestamp. Another trapper could remove the timestamp, and now I've timestamped the messages. Okay, or they can be translators like the serializer. Okay, so serializer is a translator. It translates from one kind of object to another kind of object, and then there are forwarders that just go and forward the message. Okay, and typically when you want to customize, you will be dealing with the simple customization is to replace the forwarders. Okay, so right now I have a forwarder that just simply forwards the message down. And what you can do is replace that forwarder with your own object that say timestamps it. Okay, so if you want to do something more ambitious, you could replace my serializer with your serializer. Okay, how we'll do the replacement, how we do the replacement, we'll see in a few minutes. But that's what we're going to have to replace. Okay, so this is a proxy. And this all, it seems that these two pipelines are unrelated, but actually they have to share data structure, so things get a little messy. So, for instance, there is a trapper that traps calls that are sent out. There's another trapper that traps the incoming return values. Okay? They have to talk to each other, because this guy has to block. If you're sending a function call, this guy has to block on a function call, and this guy has to unblock. Okay? So the queue that they're blocking on has to be shared. Similarly, when you go and send a proxy, if you have a remote reference, you send a proxy, a representation of a proxy object to the remote layer. The remote layer might send you back the proxy object. So you have to translate from a regular object to a proxy object here, and from a proxy object to a regular object here. So the translation between proxy objects and objects is also kept in here. Okay? And in your implementation, as Sam was mentioning, and that you have also trappers. They're not actually trappers. You're changing the ports and the notifiers. But in principle, you could have done these things through trappers also, in which case you would have the shared queue in between. Okay? So, so that's an important point. Okay? That it's not so clean. Sometimes you need to go and share, have pairs of trappers that have to work together at the same level. Okay? Of a pipeline, in the pipeline. Okay? Questions? Yeah.
So a synchronous send would be blocked at the send forwarder, the send trapper level?
Mm-hmm. Yeah.
And then that would get unblocked when the receive trapper
Exactly.
modifies the shared data.
And similarly, serialization gets done in a send trapper, and the deserialization in the receive trapper. Okay? So basically what's happened is a lot of the functionality in the ports has been put in these different trappers, and you can then change one trapper at a time. Okay? And way back we talked about why Unix is Unix, why is it called Unix, and the answer was that it's allowed to allow one thing to be done right at a time. And Dong, you gave me the answer, which you probably have forgotten. What is it in Unix that allows you to do one thing at a time correctly? Pipes. See, because you wrote the answer, you might have written it in the answer, you remember it. So, pipes allows you to do that, and basically that's what we're doing here. Pipes at a lower grain within a particular class. Okay? Pipes are expensive when you have to go between processes. You have to have multiple processes. Okay. So let's talk about the thread issue that was arising. So what about the threads in this world? We've got the send and receive pipelines. Which threads are executing these pipelines and in these various layers? So there's application code on top. And which thread is executing the application code layer? Some main, you said, or some thread created with the application. Now, as the data go down, will the threads change, you think? Okay, let's take this path. You're going down this path. Will any other thread be ever involved? NIO. You'll need to select a thread, right? But for socket, no. Okay, so the thread pretty much remains the same till you go here. Let's again think of NIO. What threads will be executing these? So NIO will be code will be executed by the selected thread. Should that thread change anytime as you go up? Application thread? Which application thread? We don't have a select call. We don't have, a receive call. What is wrong with executing all these layers in the selected thread? So we know that that's a bad idea. So where should I stop? Serialization should be done in a separate thread. RPC call should be done in a separate thread. It's got to be a system created thread, by the way.
Probably separate serialization from NIO because you don't want to have to serialize and send all at once, because one might take much longer than the other, or be,
So you're saying do the serialization in a separate thread?
Yeah, at the very least, you might want to wrote that at a higher level, but you certainly want NIO and serialization to be separate.
So just hand the data over to the serializer and it goes and forwards the thing.
Yeah.
Okay, that might be a good design principle. Okay, the principle is that don't make it wait. But remember, the application code will be executed by a system thread when you have a notify-based implicit receive. Just remember that. It will not be an application thread. That's the important thing. Okay? So if you're making RPC calls, and if that's what your system is designed for, the serialization will not take very long. You're not sending big files. Okay? So by default, now since we have all this customization, you can change anything you want to. But by default, everything gets done in the selector thread, including the RPC. But there's another alternative that's also provided in Gypsy that allows the RPC calls to be made by a separate thread. System provided thread, but a separate thread. And we'll see how to change between those two. That will give you an idea of how customization is done. Okay? So send pipeline, sender thread until NIO layer. That's what happens in Gypsy. Okay? And receive pipeline, selector thread until possibly the RPC layer. Okay? And there we have two alternatives. And Gypsy is extendable that you can change. You can create a separate thread for each call if you want to. Okay? So that's also a possibility. Okay, so to summarize, the layers are good. Okay, some systems make it clear they use layers. Other systems are not layered but could be layered, like an operating system. Unix is not layered. Okay, but it should be. Okay, and of course when you start layering things, you get into it's hard to implement. Okay, and there's more indirection, and so it could be a little slower. And then there's, just because you have layer doesn't mean that calls all go one way or the other. There's calls and upcalls. Okay, and the layers are good for many reasons. And the particular reason that we are going to be interested in is customization. And like I said, layering is tricky. So we saw with file systems that we had to break file system into regular local file system and distributed file system. And one of the innovations of RMI is that it added an object layer between the buffer layer and the RPC layer, which is great. And Gypsy says, well, let's carry the idea forward, and we allow the buffer layer to be replaced also, and we'll also allow multi-layer communication, and we'll have this implicit receive paradigm, which can be used to build explicit receives, and then we'll have trappers that can be changed individually. Okay, so that you can change one function at a time. Okay, and so that's the point here. And what I thought I'll get to today, but which I didn't, we'll get into on Tuesday, is how do we, we've got this whole architecture set up now, but we still don't know how to replace a component with another component. If you've done the assignment, you kind of know how to do it, but I haven't told you how to do it. Okay, so we'll go and look at the various alternatives possible to change those components. That will motivate what you guys have been doing, and that'll be sufficient to do the assignment. Now, I talked about call completer, receive notifier kind of stuff. The algorithm there is already on in a recorded YouTube and PowerPoint that I've made available to you. So I'm right now working at the detailed architecture level, not at the algorithm level. So if you want to do assignment number 4, the assignment tells you how to customize things, so you don't really need to know the theory or the concepts here. And the algorithm that you have to follow, or that's being followed underneath, with which you have to interface, is given in the PowerPoint that's already published. Okay. So what I'll do today is, architecture is finished. I will go and put this PowerPoint and the YouTube video and mix on the web page, and that should give you enough time to do this. Yeah, Sam.
The assignment, we just modify your version of the customized whatever.
You're welcome to start from there.
Yeah.
For the assignment. Yeah. That was the goal, that I gave you a boilerplate to do that.